All right. Last time we just got started in section 8.3. And we're going to be looking at the integral and what we call comparison test. And so, let's talk about what you're supposed to know up to this point. Chapter 8 is an incredible amount of memorization and application stuff. So you got to memorize a bunch of name series. The series that you are supposed to know at this point, the formula and how it works, is the geometric series, the telescoping series, and the harmonic series. And the harmonic series always diverges. In terms of tests, there will be 7 tests that you guys have to master. You've gotten 2 right now. The first one was called the divergence test, which pretty much said if I got a series and I noticed that the limit of the sequence part, when I take the limit as n approaches infinity, of the sequence part of that series does not give me 0, then the series is going to diverge. Okay? Doesn't say anything about what happens when the limit does go to 0. We got lots more tests coming down the road. The next one I talked about, and I just introduced it last time, was the integral test. And we'll talk more about that one today. So, again, hopefully you watched the awesome pre-section video and took the quiz and stuff. And these were the notes off of the quiz. So let's go to the little algebra review section here. Now, with the algebra review, we're going to be doing something later called comparison test. So you need to be able to compare. And what I mean by compare is a strict inequality. Greater than or less than or something or other. So, if you've got 2 functions, f of x is greater than or equal to g of x for all x in the domain. Similarly, a sequence can be greater than or equal to, an can be greater than or equal to bn if an is greater than or bn for all n in the domain. Remember, the domain of a sequence is 1, 2, 3, 4, the countable numbers. This is how we count a sequence. So we're looking at sequences, then eventually we'll be looking at series. So if you look at this one, this is pretty much straightforward. Compare the two. 5n squared plus 12, how does that compare to 5n squared plus 1? And when I mean by compare, I'm talking about inequality. Is it a less than or is it a greater than? What have we got going on here? 5n squared plus 12 compared to 5n squared plus 1. Well, obviously the plus 12, the 5n squareds match up. The 12 is bigger than the 1, so this would be a straight greater than. Does that make sense? This sequence of numbers is going to be bigger than this sequence of numbers, is what we're saying, as n goes from 1, 2, 3, 4, all the way down the line. Now compare this guy. What about 1 over 12n plus 1, 5n squared plus 12 as compared to 1 over 5n squared plus 1? Now here's the deal. When one is bigger than the other, but when you make fractions, 1 over something really big is what? Really small. So when you start talking about fractions, even though the 5n squared plus 12 is greater than 5n squared plus 1, when I do 1 over 5n squared plus 12 would actually be less than 1 over 5n squared plus 1. The bigger the denominator, the smaller it is. This is going to be, again, something very helpful when we get you guys into what we call a comparison test, which hopefully I'll get to today. So, look at the relationship of how polynomials and then fractions, rational expressions work. And again, we're talking about sequences with this stuff. All right, this is what I talked about last time, and we did one example before I let you guys go, and that was this, the integral test. And this was number 2 out of the test you're going to have memorized out of the Big 7. Now, it says this, very straightforward. If you got to see, remember, we're starting with a series. The sum as n goes from, let's say, 1 to infinity of an. So I've got a series right here. And what we're going to do here is we're going to let an look at it as a function of n. So this is going to be a function now, f of n. This is f of n is what we're looking at. And therefore replace n with x to make it a real function. And it's got to be positive, decreasing, and continuous. Positive means it's got to be above the x-axis when you graph it. Decreasing means this derivative is going to be negative. It should be sloping down, because if it slopes up and you're going to be integrating, adding it up, it's going to blow up to infinity. It's got to be actually going down. It's got to be, as you add smaller and smaller numbers, it's got to, hopefully you can be able to add it to be able to get a number out of it. So it's got to be positive, decreasing, and continuous for x's that are greater than or equal to 1. Now here's the big deal. As you would expect, there's a direct relationship between integration and summation. It's called Riemann sums. So replace the summation with an integral. So if you make this an integral from 1 to infinity of f of x dx, and it converges, aka the integral goes to a number. That's that chapter 5.10 stuff that we did. Okay? If you integrate this thing and it converges, then the series is going to converge. Actually, it's what is it, section 6.6, I believe it was, that we did actually this stuff. The integral, basically, this is an improper integral because of the infinity. So we got to make it a proper integral, but you're going to evaluate the integral, and if the integral converges, here's the deal: the series converges. If the integral diverges, the series diverges. They're going to do the exact same thing. Now, when the integral converges, when you integrate and you get the quote area under the curve, it's a number. What's the series going to converge to? I have no idea. I can tell you it's going to be less than this number, but it won't be this number, because this is area under the curve. A series only gives you the values at 1, 2, 3, 4. So there's lots of gaps in this thing. So the series is always less than the integral. So I did this problem for you guys last time. This is the sum as n goes from 2 to infinity of 4 over n times the natural log of n cubed. Rule 1 about the integral test. I got a series and I want to know, and here's directions. And listen up and listen good. From chapter 8.2 to chapter 8.3, I've changed one thing: the directions. In chapter 8.2, I said this: here's the series. Does it converge or diverge? And if it converges, what does it converge to? Find its sum. There's only two series we know exactly what they sum up to without much effort: geometric series and the telescoping series. So with those directions, you know I either got to give you a geometric series or a telescoping series, or the series diverges and you're done. So look for geometric and telescoping. In chapter 8.3, now we're going to get a much harder series, and all we're interested in is this: does the series converge or diverge? That's it. The answer is going to be the converge, or the answer is going to be diverge. But you just don't get free points here by guessing correctly. You actually have to prove it. Prove it with your statements of by the integral test, by the divergence test. You got to actually give me a test and a statement of reason behind your answer. So you're getting into a little bit of this math proof concept here. So, first rule of integral test. Number 1, make sure if you convert the series over to an integral, you can actually integrate it. You can't use the integral test on something you can't integrate. Use your logic here. So in this problem, that was the first question I had was, okay, this is 4 over n times natural log of n cubed. So the denominator is getting bigger and bigger and bigger as you actually plug in values of n starting at 2. And so that means it is a positive, because all the terms are going to be positive. It's decreasing because with the denominator gets bigger, the fraction gets smaller. And it's a continuous function because the natural log of n, as long as you're not plugging in 0 or 1 in this case, or anything less, this is nice and continuous. And most important, when I convert him to an integral with the appropriate technique of integration, I use u substitution on. I let u equal the natural log of x, d equals 1 over x dx. I substitute it. I can integrate. This becomes integral of u to the negative 3 du, which you integrate and get negative 2 over u squared. And then you back substitute. This is negative 2 over the natural log of x squared. And then I do my limit, and this is improper, so I got to take my limit as a approaches infinity of negative 2 over natural log of x squared, what I integrated it be from 2 to a, plug in top, plug in bottom. And when I did that, I end up getting a number. And therefore we say the integral converges to, when you integrate it, to this particular number. But now, here comes your test. The question wasn't, can you actually integrate this guy? The question was about this series. But since the integral conversion of that series, when you integrate it, it converges. That means the integral converges by the integral test. That's the whole deal right here. And I proved that this thing is actually going to converge. Take a look at this next guy. Now, this is a guy you should recognize. So if I give you this problem, the sum as n goes from 1 to infinity of 1 over n. I ask you a straight question: does this series converge or diverge? It's a no-brainer as long as you actually studied. What kind of series is this guy? This dude's got a name. What's his name? Harmonic series. And what does the harmonic series do? Diverges. You're done. Harmonic series diverges. Win the game. Next problem. But the problem is, I told you to prove it. I never proved you the harmonic series diverged. I just told you it diverged and gave it a name. Harmonic series, it always diverges. We're going to prove it. How am I going to prove it? I'm going to actually use the integral test on this guy. So here we go. 1 over n is always positive, and you notice as n gets bigger, it decreases. So I'm allowed to use the integral test on this one. So I'm going to convert this to an integral. This becomes the integral from 1 to infinity of replace n with x, 1 over x dx. Now there is the equivalent integral of this sum as n goes from 1 to infinity of 1 over n, 1 over n. So this is the integral version of it, but it's improper. I've got to make it proper. So I'll pick my favorite letter. Showing your work is everything in calculus. The limit as a approaches infinity of the integral from 1 to a of 1 over x dx. With me? Now integrate it. A no-brainer. This is basic rule 101, or actually section 5.1 in this class. What's the integral of 1 over x dx? Natural log absolute value of x. So this is equal to the limit as a approaches infinity of the natural log absolute value of x evaluated from 1 to a. According to the fundamental theorems, you plug in top minus plug in bottom. This is equal to the limit as a approaches infinity of the natural log absolute value of a minus the natural log absolute value of 1. Plug in top minus plug in bottom. But what is the natural log of 1? That's a natural number you're supposed to know from high school. Natural log of 1 is 0. So this is equal to the limit as a approaches infinity of the natural log absolute value of a. And then evaluate the limit. Plug it in. This becomes the natural log of absolute value of infinity is infinity. But what is the natural log of infinity? Things you're supposed to know from Calculus 1, day 1 in that class, chapter 1.3 or something, or 1.4. The natural log of infinity is infinity. And you got an infinity answer, which means the integral is divergent. Therefore, this is all your work right here. Therefore, your conclusion is, remember your series, this is the sum as n goes from 1 to infinity of 1 over n. Well, since the integral diverged, guess what the series is going to do? Is divergent by the integral test. Harmonic series diverges, okay? We just proved that the harmonic series diverges, but we actually did it through the integral test. This is your statement of proof. So get used to kind of being a little wordy about your problems. This is what we're looking for, this idea of math proof. But every problem I'm going to give you from this point until past 8.4 is here's the series. Does it converge or diverge? And why? Okay, you got to tell me why. Just don't flip a coin and guess at it. Maybe you'll make a 20 on the next test. Does that make sense? You actually got to state why. All right. But look at the comparison. Now look at this guy. This guy here is the sum as n goes from 1 to infinity of 1 over n squared. Something extra has been added to it. The last one was 1 over n. This is not the harmonic series because it's got a power, 1 over n squared. But the question is still the same. Does this series converge or diverge? Well, I'm going to convert this guy over to an integral and apply an integral test. So this becomes the integral from 1 to infinity of 1 over x squared dx. I'm going to convert this improper integral because of that infinity to a proper integral by making a limit. Take your limit, it's my favorite letter, a approaches infinity of the integral from 1 to a. I'm going to clean this up. I don't like 1 over x squared. I don't like stuff in the denominator with a power. Bring it to the top. It becomes x to the negative 2 dx. First rule integral, add 1 over add 1, power rule here. Here it is. Integral x to the negative 2 is going to be x to the add 1, negative 1 over negative 1, evaluated from 1 to a, with, of course, your limit as a approaches infinity out front. So when you clean this up, this is the limit as a approaches infinity of negative 1 over x, evaluated from 1 to a. Now, according to the fundamental theorem of calculus, we evaluate it by plugging top minus plugging bottom. This will be equal to the limit as a approaches infinity of negative 1 over plug in top a minus negative 1 over plug in bottom 1. Cleaning this up, this is equal to the limit as a approaches infinity of negative 1 over a plus 1. negative, a negative 1 over 1 is plus 1. Now take your limit as a approaches infinity. First rule of limits is plug in the number. So this is negative 1 over infinity plus 1. Notice I don't write limit anymore once I plug in the infinity. But what's 1 over infinity go to? This is 0. Plus 1 equals 1. Therefore, the integral converges to 1. The integral converges to 1. Does that make sense? Therefore, 3 dots in a triangular fashion means therefore the actual series, the sum as n goes from 1 to infinity of 1 over n squared, is convergent by the integral test. Dr. Taylor, what does it converge to? I don't know. Well, actually, I got an idea. I've studied these things before, but it's a royal pain to actually prove this to you. It's some kind of, it converges to an irrational square root of pi over 4 or something like that. But I'll go back and memorize that one. But what is it actually converging to? I don't know, right? I gotta go look it up, but I don't know. I can tell you this, it's gonna converge to something less than 1, but that wasn't the question. The question is, does it converge or diverge? This thing's gonna converge. When you add this stuff up, it's gonna add up to a number. Okay, and it converges to something less than 1, but what exactly is this number? It's some awful irrational and higher level math. We can prove that kind of stuff to you. Does that make sense? Did I lose you guys anywhere? But, so notice the last two problems. I had 1 over n, sum of 1 over n, which was the harmonic series, which diverged. And then I just did the sum of 1 over n squared, which actually converges. I told you guys last time that the harmonic series is this line drawn in the sand, that if you fall on one side versus another, you're either going to converge or diverge, and that line is the harmonic series. The harmonic series diverges, and it's basically the power on that end. So we have something called a p-series. This is your next name series, so put it under a list of names that you have memorized. You know geometric series, you know telescoping series, you know harmonic series, and now you're going to know the p-series. Because the p-series is a series that's in this form. The sum as n goes from 1 to infinity of 1 over n to the power p. This power series, or p-series, is going to converge if p is greater than 1, strictly greater than 1. So when that power on the n in the denominator is bigger than 1, the series is going to converge. If the power p of in your denominator is less than or equal to 1, it's going to diverge. And notice when it's equal to 1, it's actually the harmonic series. That's that line right when you start the divergent series. So if your power of sum of 1 over n to the p, if your power is less than 1, less than or equal to 1, it's going to diverge. If it's greater than 1, it's going to converge. So take a look at these guys. Determine whether each of the following series is convergent and divergent. First rule of series is sum as n goes from 4 to infinity of 12 over n cubed. First things first, 12 is a constant. What do you get to do with constants? Out front. So this is 12 times the sum as n goes from 4 to infinity of 1 over n cubed. It doesn't matter if you start at 1, 2, 3, it is still called a p-series. This guy in times 12, no one cares there. This is all about the 1 over n to the p. This is a p-series, and this is what you have to tell me. What does p equal to? What's your power? 3. How does your power compare? P is bigger than 1, so it is convergent. This is a convergent p-series. P is 3. As long as it's bigger than 1, it's a convergent series. If your power is less than 1, it diverges. Take a look at this guy. The sum as n goes from 1 to infinity of 108 n to the 4th. You look at this thing and go, is that a p-series? Yes, it is. First things first, constants go out front. So this is 108 times the sum as n goes from 1 to infinity of n to the 4th. But to be a p-series, you got to write the series as the sum of 1 over n to a power. So I want to put that n in the denominator. When I put this n to the 4th in the denominator, what does it become? 108 times the sum as n goes from 1 to infinity of 1 over n to the negative 4. Does that make sense? I put him in the denominator, but now he's got that p-series look to him. And this is a p-series. However, what is p equal to? negative 4, which is less than or equal to 1. So the series is divergent. This is a divergent p-series. The sum is n goes from 1 to infinity of 108 n to the 4th. Does that make sense? And this p-series is kind of a powerful dude because the next test we're going to be looking at is called a comparison test. So if you ever ask, what do you ever compare to? Number one thing I'm going to compare to are p-series. So this test, so in terms of test numbers, congratulations, you made it up to test number 3 in terms of stuff you've got to have memorized. This is called the direct comparison test. Web work is going to call this one just the comparison test. But actually, there are 2 types of comparison tests in Chapter 8.3. There's the direct comparison test and the limit comparison test. Web work calls the limit comparison test the limit comparison test. But when it calls the direct comparison test, they just say the comparison test. We're going to use its proper name, direct comparison test, but we're math people. Can't handle too many words. Direct comparison test. We shall shorten it to the DCT, direct comparison test. We abbreviate everything in math. There it is. All right, so here's what the direct comparison test says. It is this. For 2 sequences, AN and BN, and here it comes, such that 0 is less or equal to AN, which is less or equal to BN. Both sequences are positive, but the BN is on top of AN. So you got this comparison. You got one on top, one on bottom. BN is bigger, AN is smaller, but they both got to be positive for right now. All we talk about is positive term series here. In this case, sequences. Now we're going to look at a series. So, number 1, if the sum as n goes from 1 to infinity of BN converges, that will automatically imply the sum as n goes from 1 to infinity of AN also converges. And number 2, if the sum as n goes from 1 to infinity of AN diverges, that implies the sum as n goes from 1 to infinity of BN also diverges. Let me explain it to you in a little bit better English. Here's the deal. We're doing a comparison test. See, this AN and BN, one of them is going to be known and the other one's not going to be known, but we can compare. And I'm always trying to find out what's happening to the unknown dude. So, I've got AN and BN. BN is on top and AN's on bottom. If the BN is the known series and it's on top, and if the guy on top converges, then anybody below him, the sum as n goes from 1 to infinity of AN, must also converge. When the guy on top, when you sum him up, and he converges, adds up to a number, then anybody below him has to add up to a number. This is a comparison test, but on this one, with the converging, I got to have the guy on top converges. Anybody on top that converges, anybody below him is going to converge. But if I flip it up, and I've got this, if the sum as n goes from 1 to infinity of AN diverges, if the guy on the bottom, AN, is a series that I know what it does, and it diverges. If the guy on the bottom diverges, that will imply anybody above him, the sum as n goes from 1 to infinity of BN, will also diverge. So if the guy on top converges, anybody below him converges. If the guy on the bottom diverges, anybody above him is going to diverge. If you're sitting on top of something that blows up, you blow up too. That's the part number 2, what we're talking about here. Does that make sense? It's a comparison. But you got to get who's on top and who's on bottom. Now, what does this theorem say about if the guy on the bottom converges? What does it say about the guy on the top? Absolutely nothing. If the guy on the top diverges, what does it say about the guy below him? Nothing. You've got to get it in the right order. If the guy on the bottom diverges, then the guy on the top must diverge. If the guy on the top converges, then the guy on the bottom must converge. That's the only thing this theorem tells you. It's called the direct comparison test. So, tell you what, I'm going to skip over this one right here for just a second. Don't worry, I'm coming back to them. I want to look at this one because it's a little easier for me to explain as we do these problems. So I want to get the easy ones first, and I'll go back and look at the, quote, more challenging ones here. All right, so here's the deal. The question always is, when you're doing a comparison test, a direct comparison test in particular, what am I going to compare to? And I got to be able to explain it mathematically. So look at this guy. This is the sum as n goes from 1 to infinity of 5 over n squared plus 4. 5 over n squared plus 4. Now I want to compare this guy. So the 5 over n squared plus 4 is going to compare to 5 over n squared. How? What I'm really going after is I see that n squared, I'm thinking p series here. Constants being multiplied don't bother me. Just hold the constant there. It's the plus 4 that's my problem. So what's the relationship between the two? Well, it's pretty much the same fraction except for this one has plus 4 added to it. When you add something to the denominator, it makes the denominator bigger but makes the overall fraction what? Smaller. So this 5 over n squared plus 4 is less than or equal to 5 over n squared. Because you added something to the denominator, makes the denominator bigger, makes the overall fraction smaller. Now, let's talk about this dude. Who is this dude? But as the sum as n goes from 1 to infinity of 5 over n squared. Look at this series. Now, I put the sum back on this guy. This is a series. Where do constants get to go? Out front. So this is equal to 5 times the sum of n goes from 1 to infinity of 1 over n squared. What's this guy's name? This is a p series. Times 5, no one cares about. P series. What is p equal to? 2. 2 is bigger than 1. What is it going to do? Converge. So, this is a convergent p series. Convergent. So, the guy on the top converges. According to this theorem, when the guy on the top, the Bn converges, what does that imply about the guy below him? He's also going to converge. Therefore, you had to state this. This is a p series that converges. This guy is above this guy. Therefore, the sum as n goes from 1 to infinity of 5 over n squared plus 4 is convergent by the direct comparison test. And there's my statement of proof. But it's more, I had to show you the inequality. I had to talk about the series of, in this case, the top guy being a p series, tell me why he converged, and then imply by the test that I used. I'm using the direct comparison test, DCT. Does that make sense? Now look at the next guy. I got the sum as n goes from 1 to infinity of 3 divided by 4n minus 1. Okay? Well, as 3 over 4n minus 1, it's that minus 1. If that wasn't there, then this thing is going to be a series. I can pull out my constant. What kind of series would this guy actually turn into if you pull out the 3/4? Again, dropping the 1 here. What kind of series is this guy? Harmonic. It's a p series. P equals 1. You can say that. That's kind of lame. It's called a harmonic series because it's got a name. It's when the harmonic series diverges. But subtracting 1 from this guy, compare that to, if the 1 wasn't there, 3 over 4n. How does this guy? If you subtract 1 from the denominator, it makes the denominator smaller, but makes the overall fraction what? Bigger. So this 3 over 4n minus 1 would be greater than or equal to 3 over 4n. But as the sum as n goes from 1 to infinity of 3 over 4n is equal to, pull out your constant, 3/4 times the sum as n goes from 1 to infinity of 1 over n. And what kind of series is this guy? That 3/4 don't matter. Look at sum as n goes from 1 to infinity of 1 over n. What kind of series is this guy? Harmonic series. You can say he's a p series, p equals 1. That's fine. But who are we kidding? It's a harmonic series which diverges. Thus, therefore, you write the word therefore if you don't want to put the 3 little dots there. Therefore, the sum, this guy right here that we're after, as n goes from 1 to infinity of 3 over 4n minus 1 is, since the guy on the top, excuse me, let me rephrase that. Since the guy on the bottom diverged, that forces the guy on the top is divergent by the direct comparison test. He directly compared these two guys, and this guy is very, very close to it. He's not a harmonic series, but if you just get rid of that little constant minus 1 problem and pull the other constant out front, he is an actual harmonic series. So this is called the direct comparison test. So if you look at the last 2 examples, I compared it to p series. P series, real important. We love p-series because that's why half these problems, my goal is to get you guys to actually look at it and do what we call the mental comparison test, which is actually not in your textbook, but it's something you're supposed to learn how to do. You can look at these darn things and tell what they're going to do even before you start. That's what we're after. Now, look at this guy here. The sum as n goes from 1 to infinity of 3 over 2 raised to the n minus 1 plus 5. Well, if that plus 5 wasn't there, so let's talk about it. 3 over 2 to the n minus 1 plus 5. How would that compare to 3 over 2 to the n minus 1 without the plus 5? It's these plus constants that are killing me. So I'm trying to get rid of them. What's the relationship between these two guys? Well, I added 5 to the denominator, which made the denominator bigger, but this overall fraction would be what? Smaller. This 3 over 2 to the n minus 1 plus 5 is actually less than, you can say less than or equal to, all we care about, is 3 over 2 to the n minus 1. Now let's talk about this series. And as the sum as n goes from 1 to infinity of 3 over 2 to the n minus 1, that's equal to the sum as n goes from 1 to infinity of 3 times 1 over 2n minus 1. I'm trying not to skip any steps because I want to show you the algebra here. What did I do? I pulled my constant out in front, but I didn't pull him completely out in front. I put him right in front of this guy, and just when you pull him out in front, he makes a 1 over. And by the way, 1 to any power is always 1. So this is the same thing as the sum as n goes from 1 to infinity of 3 times 1 to the n minus 1 over 2 to the n minus 1. Which makes this series the sum as n goes from 1 to infinity of 3 times 1/2 to the n minus 1. What kind of series is this guy? You don't always compare just a p-series. What kind of series does this do? It's a series of numbers raised to powers of n times a constant. No one cares about those guys. Numbers raised to power of n is called what? Geometric series. This is a geometric series. And A is equal to 3. R is equal to 1/2. The absolute value of R, which is equal to absolute value of 1/2 equals 1/2, is less than 1, which means, again, you've got a lot of tests here. This is the geometric series. When your R is less than 1, what does it do? Converges. Now, I know it converges to, it's convergent. It converges to A over 1 minus R. I don't care what it converges to. I just want to know this thing converges. This is a geometric series that converges. It's a convergent geometric series. Your R is 1/2. Absolute value of R being less than 1, it converges. Therefore, 3 dots in a triangular fashion means therefore, the sum as n goes from 1 to infinity of 3 over 2 to the n minus 1 plus 5 is convergent. Why is it convergent? Well, the guy on the top converges, according to my theorem. When the guy on the top converges, that forces the guy on the bottom to also converge. It's convergent by the direct comparison test. The problem with the direct comparison test is very simple. You got to make sure that inequality works just right. How many times have I seen students sit there and tell me, the guy on the bottom converges, therefore the guy on the top is nothing. If the guy on the bottom converges, you can't say squat about the guy on the top. And vice versa. If the guy on the top diverges, the guy below him may converge or may diverge. I don't know. I can't actually force it by the direct comparison test. Let's take a look at that first one that I skipped over, just to show you guys. I got the sum as n goes from 1 to infinity of, and this one's a trick. I want you to pay attention to this, because I'm doing two things on this guy. It's the sum as n goes from 1 to infinity of n squared minus 1 over n to the 5th plus 5. I'm doing stuff to the numerator and I'm doing stuff to the denominator. But let's just compare this guy. This n squared minus 1 over n to the 5th plus 5. I'm going to compare it to just n squared over n to the 5th. Two things. First off, you subtracted 1 in the numerator. In the numerator, subtract 1. When you subtract 1 in the numerator, it makes the numerator smaller, right? So this fraction compared to this guy is actually going to be less than. And gets better. I added 5 to the denominator. When you add 5 to the denominator, it makes the denominator bigger, but it makes the overall fraction what? Still smaller. So this guy is strictly going to be less than the n squared minus 1 over n to the fifth plus 5 is strictly less than n squared over n to the fifth. So this is an important problem because you want to when you clean up the constants, that pluses and minuses, if you can directly compare, you can clean this stuff up. What's n squared divided by n to the fifth? That does reduce. This is equal to 1 over n to the third power. And as, I'll draw my little line down here, and as the sum, as n goes from 1 to infinity, of 1 over n cubed. What's this dude's name? P series. P equals what? 3. And when your P is bigger than 1, is what? Convergent. Therefore, the sum as n goes from 1 to infinity. So the guy on the top converges. Therefore, the guy on the bottom, n squared minus 1 over n to the fifth plus 5 is convergent. The guy on the top converges. The guy on the bottom converges. Is convergent by the direct comparison test. But notice how I had to get it down to the n squared over n to the fifth and reduce it to that to 1 over n cubed to show you it's a P series. That's what we're comparing to. Yeah, Rachel.
What if it was n to the fifth minus 5?
What if it was n to the fifth minus 5? What you would do in that case is go to the next test. Okay. It's a lame, very good question. But that was the last thing I was telling you about this guy. This is the direct comparison test. What does that mean? You got to be able to directly compare this stuff. So every one of these problems have been worked out just perfectly that they added 4 to the denominator, makes the denominator bigger, makes it smaller than the convergent guy. What if you subtract 1, but that happens to be a divergent series you're comparing it to? So when you subtract 1 from the denominator, it makes the denominator bigger, which is going to force this guy to diverge. Every one of these direct comparison tests have been structured just right that the guy you want to compare to, it converges and he'll be on top, or if you want to compare him to something that diverges, he'll be on the bottom. What if it's the other way around? You can't do the direct comparison test. And because of that, we have something called the limit comparison test. So these guys are just right. Now, honestly, so your test number 4 over here is going to be the limit comparison test. And because we're math, what do you think we're going to code this guy as? That's right, the LCT. Now, here's the deal. Now, look at this one right here. The limit comparison test is actually, in my mind, is a little bit stronger. I only used the direct comparison test when I can get a beautiful, I added 5 to the denominator to something that was going to converge, makes the denominator bigger, overall fraction smaller. I mean, it's almost a very quick, I can compare these two and get that inequality. If you're spending more than 10 seconds to compare an unknown to a known, you probably should not be using the direct comparison test. The limit comparison test I use about 90% of the time. A direct comparison test I use about 10% of the time because I see something very quick that clearly this guy that I want to compare to is bigger, or the guy I'm going to compare to is going to be smaller. But you got to figure out what you want to compare to. Let me explain the difference. In the limit comparison test, now there's a lot more work to show, but it's a little more powerful because you don't have to worry about the inequality like I did in the last one. Here it is. It says this: for two series, the sum as n goes from 1 to infinity of an, and sum as n goes from 1 to infinity of bn are two positive term series. So we don't worry about summing up negative stuff. It's got to be positive term series. And here's the deal. I want to let you know in terms of English here. An, I'm going to call him the unknown guy. An is your unknown series. Bn is your known series. What known series do you know? You know geometric series, you know telescopic series, and you know P series. And P series is going to be big with this stuff. So you know 3 big series here. And mainly P series is one of our big guys. All right. You know this guy. And here's the deal. If you take the limit as n approaches infinity of the ratio of the sequence, the unknown an sequence over the known bn sequence, and you get a constant. When you take your limit as n approaches infinity and you get a constant. The constant can't be 0 and it can't be infinity. You got to get a number, c, not 0 and not infinity. So c's got to be greater than 0 and finite, not 0 and not infinity. You get 45. You get a number. I don't care what the number is. You get a number. 1 is a lot of times what you get, but maybe 2, 45, 17. Don't care. You get a number. Then both series will either converge or both diverge. So what you're comparing to, this is a known series that converges. Then if you get this limit as n approaches infinity of the an over b and you get a constant, if this converges, then the an is going to converge by the limit comparison test. If you decided to compare it to a divergent series, and you can show me this limit as n approaches infinity of the ratio of the an unknown sequence to the known sequence, and I get a constant, then that will force the other series, the sum as n goes from 1 to infinity of an, to also diverge. So the trick is, who am I going to compare to, and then I got to show my limit. So I try to start you out with this guy right here. It's the sum as n goes from 1 to infinity of n squared plus 2n minus 5 divided by n to the fourth plus n plus 7. All right, in this one, in terms of a direct comparison test, you're already in trouble. So if you try to compare it to, like we did in the last one, the n squared over n to the fourth type thing here, well, you're adding 2n to the denominator, makes the denominator bigger, then you're subtracting 5, which makes it back to being smaller. Okay, and then you add it into the denominator, makes it denominator bigger, and denominator bigger makes it front. Is it going to be smaller or greater than? With the plus and the minus, there's no way you get inequality on this thing. You're taking, and that's typically most of them, 90% of them, you can't get inequality quick. But here's the deal. Instead of doing the less than or greater than, I'm going to do the famous squiggly equal to. That means it's approximately, and it's going to be the sum as n goes from 1 to infinity. And what do you got in this problem? You have got a polynomial divided by a polynomial. When you have polynomials divided by polynomials, even though they're sequence type things here, it's the leading term that's in command. Look at your numerator polynomial, n squared plus 2n minus 5. Who's in command? Who's the highest degree term? What is it? It's the n squared. He's the guy in charge. Rest of it I don't really care about. Look at your denominator. It's n to the fourth plus n plus 7. Who's the guy in charge? The degree term, what is it? N to the fourth. This is what you should compare to, the leaders. Don't need a constant. The constants you can just drop off now because you're not worried about an inequality. You just got to figure out who to compare to. Now clean this guy up. What is the sum as n goes from 1 to infinity of n squared divided by n to the fourth? That's the same thing as the sum as n goes from 1 to infinity of 1 over n squared. N squared, n to the fourth, n squared cancels with 2 of those n's out of the n to the fourth, leaving 2 left over. N squared. It's 1 over n squared. This guy's got a name. What's this guy's name? It's P series. P is equal to 2. Got to tell me that. And what is P equal to, being bigger than 1, going to do? Converges. Okay? Right here is where most people mess up. Because you got to have this stuff memorized. And what you're getting confused is, well, I thought it was less than 1 and it converged. No, that's geometric series. The geometric series, if R was less than 1, absolute value of R, was less than 1, geometric series converges. With P series, the P has to be greater than 1 to converge. Get them straight in your head and don't screw it up. Okay? So a lot of definitions you guys need to know. So here we go. This is a P series, P equals 2, which is greater than 1, so this P series converges. Now, what you're going to do here is, now, you're going to take the limit, show the limit as n approaches infinity of the ratio of the unknown, which is the big guy typically, over the known, which is the small guy. Unknown over known. The unknown is the n squared plus 2n minus 5 divided by n to the 4 plus n plus 7 divided by the known series. The known series is, the sequence part of the known series is 1 over n squared. It's the bn over an, or an over bn. Look here. This is the guy that's known. The known sequence always goes in the denominator. Makes the math a little easier for you. Does that make sense? Now, take the limit as n approaches infinity. But before you do that, clean it up. What do you do to clean up a fraction divided by a fraction? What am I going to do? Invert and multiply. Multiply by the reciprocal. So this is the limit as n approaches infinity of n squared plus 2n minus 5 divided by n to the fourth plus n plus 7 times, invert and multiply, that'll be n squared over 1. Now, clean it up. I'm going to distribute. This would be equal to the limit as n approaches infinity of n squared times n squared is n to the fourth plus 2n times n squared is 2n cubed minus 5n squared divided by 1 times n to the fourth plus n plus 7 is n to the fourth plus n plus 7. I just cleaned it up. Now take your limit. And I want to remind you something, brother. You are in Calculus 2. We expect a little better from you people. What I mean by that is you can also cut some corners on some stuff because you're supposed to know more than most folks. Here's the deal. If I take limit as n approaches infinity, and I plug in infinity, I get infinity to the fourth plus infinity cubed minus 5 times infinity squared. I'm going to get an infinity over infinity to the fourth plus infinity plus 7. It's going to be infinity over infinity. So what am I going to do? L'Hopital rule it. Drew the top, 4n to cube plus 6n squared minus 10n divided by derivative of n to the fourth is 4n cubed plus 1. Then you plug it in, you get L'Hopital it again. So you take derivative of the top over derivative of the bottom again. And again, and again, and again. You keep getting infinity, infinity, but it keeps knocking you down until you get the answer of what would the actual answer be. I'm not doing L'Hopital's rule. You should actually know what the answer is. You'll notice that the degree of the numerator is 4. The degree of the denominator is 4. So when the degree of the top is the degree of the bottom, the answer is what? Ratio of the leading coefficient, which is officially 1 over 1. The answer is 1. And you didn't have to do all the L'Hopital rule. We expect you guys to do that. We will give you a bye on this one because this isn't Calculus 1. This is Calculus 2. When the degree of the top is bigger than the degree of the bottom, you get infinity or negative infinity. When the big degree of the bottom is bigger, you get 0. But when they're the same degree, and this is what's going to happen with this limit comparison test, because that's what you want to compare to, you're going to get the ratio of leading coefficient. In this case, it's 1 over 1, which is 1. So this, therefore, C is equal to 1. That constant. It's not 0 and not infinity. And thus, the sum as n goes from 1 to infinity of n squared plus 2n minus 5 over n to the fourth plus n plus 7 is what? What did you just compare it to? We compared it to the sum of 1 over n squared. A p-series, p equals 2, which converges. And when you compare to something that converges and you can show you get a constant off the limit, what's it going to do? It's going to converge by the limit comparison test. And notice something or other. Okay, it looks like there's a lot more work with this one. Yeah, you're right. There's a little bit more work with showing this limit aspect of it. But if you go back over here to the direct comparison test, this was short work if you can get that inequality working for you into knowing what to compare to. Getting that inequality, what happens if I had this problem right here? See this problem right here? I'm going to pull a Rachel on you on this one. What if the sum as n goes from 1 to infinity, 5 over n squared minus 4 instead of plus 4? Well, subtracting 4 from the denominator makes the denominator smaller, makes the overall fraction bigger. It's going to be bigger than this guy. And bigger than converging is going to do what? Nothing. I couldn't actually use the direct comparison test because I can't get my inequality the right way. I know what to compare it to, but to be comparing to convergent, I got to make sure it's smaller. If it's bigger, I can't use the direct comparison test. The limit comparison test usually works in those cases. So you have to see it just right to get the direct comparison test. We'll study more on the limit comparison test next time, and then we will do some more tests like the alternating series test. Yay! We're going for more stuff. See you guys then.